So this lecture we continue to study the common source amplifier configuration, and these are the numbers we'll use as last time. So last lecture we had studied this circuit in detail, and we had found by the end of the last lecture that this circuit can give a gain of about 60, 58 to be precise. That is the highest gain we can get. But remembering that our goal in this course is to design an amplifier with a gain of about 10,000. The next question we ask is, well, can we do something to this circuit so as to obtain a higher gain? Alright, so let us think about this and let us see the expressions and all. So we had derived this expression last time for the circuit. VO by Vin is minus GM-RD, and GM is 2ID over VGS minus VT, and then ID-RD is the voltage drop across the resistor RD, so we can write that as the VDD minus VO. And we rewrite this in terms of VO, so we say VO is equal to VDD minus ID-RD. And we saw last time that in order to increase the gain, we can increase RD, but as we increase RD, VO, the DC drain voltage, decreases, and therefore eventually the transistor goes into triode. Now let's think about another possibility which we really didn't talk about last time. Is suppose we want to keep VO constant as we increase RD so that the gain increases. What we can do is we can increase VDD as much as we increase RD so that VDD minus ID-RD stays constant at VO, and if VO is constant, then the transistor does not go into triode. Let us look at this graphically. So I assume you are all familiar with the load line, but let me go through this quickly. So this is a plot. There are two plots here. This is ID versus VD for the MOSFET. The output characteristics for different values of VG, so that these blue are 3 different values of VG, so that is the output characteristic of the MOSFET. And this red line is the Ohm's law for the resistor RD. So the equation for the resistor is that current in the resistor is equal to VDD minus VD over RD. And what we are plotting here is the current IRD on the y-axis and VD on the x-axis. So that we get IRD versus VD a straight line with a negative slope. The slope is minus 1 by RD. You've all seen this before. And so the intersection of the red line and the blue line give us the DC operating point. Now, which blue line? There are 3 blue lines here. In fact, there are infinitely many blue lines possible. This is a blue line corresponding to the gate voltage we have applied. So we have applied, how much have we applied? Let us see. 0.5 volts, right? So the threshold voltage is 0.4. So we have an overdrive of 0.1 volts. So this blue corresponds to a VG of 0.5 volts. Okay, so now we say, well, we want to see what happens if we increase the value of RD. Now the slope of this line is 1 by RD, so the slope will become smaller. So here is another plot. So if we make RD 48 kilo ohms from 4.8 kilo ohms, then the load line corresponding to the 48 will be this red line, so that the VO, the DC drain voltage, stays the same, but the slope has become much shallower, and therefore this will give us a much higher gain. Of course, the price we pay, as we just saw, is that so this load line has to meet the x-axis. Where it meets, the current is 0, and when that current is 0, we get the VDD. That is the VDD we must apply to get this characteristic. So here is the same plot, but now we've extended the VD axis so that the red line can meet the x-axis. So what we see is that we need a VDD supply voltage of about 25 volts in order to get a higher gain with the same DC operating point. Now, of course, This is only theoretical. In practical situations or in real systems, VDD first of all cannot be this large. Most electronic circuits do not operate at 25 volts. They operate at 3 volts or 5 volts. Hopefully sometimes 5 volts, and now of course they are coming down to 1.5 and all that. The other concomitant issue is that as circuit designers, we really don't have control over the value of VDD. VDD is decided by the system requirements and the system configuration, and the system designer typically tells the circuit designer, this is a VDD, you give me a circuit that works at that VDD. So neither do we have can we make VDD large simply because integrated circuits do not work at such large VDDs, nor do we actually have control over the exact value of VDD. We are told as analog circuit designers by the system designers. Okay, a point on the side, there are of course integrated circuits that can operate at much higher voltages, 60 volts, 100 volts. MOSFETs I should say, and integrated circuits both. But these are special purpose MOSFETs. They have very thick oxides, and they have to be designed such that they can withstand high voltages and they don't break down. But one doesn't excuse me one doesn't use such high voltage MOSFETs for a usual amplifier design because they have their own limitations. The GMs are small and so on and so forth. So alright, so we are constrained in our VDD to, let us say, 3 volts. So here is the next question we ask. So we say, well, this is what we would like. We would like the load line to be shallow, but we are not able to use this resistor as the load because we'll require very high VDDs. So we say, what if our load line could be like this? It is shallow over this region, but then somehow magically the load line or the IV characteristic of the load falls off to 3 volts as it approaches VDD. Wouldn't that be nice? Then we can get high voltage gains without requiring large VDDs, right? Now what is this device? What device has this IV characteristic? It is a PMOS. Alright, so this is a PMOS IV characteristics drawn on the IDVD plot of an NMOS. So when the drain voltage of a PMOS is 3 volts, okay, let us see the circuit actually. So here is a circuit. So this is a circuit. So instead of a resistor, we connect a PMOS here. And so what we have plotted there is VO versus ID. So when VO is 3 volts, the drain source voltage of the PMOS is 0. So no current flows through it. And as VO reduces, so let's go back here. So as VO, so we start from 3, and if we reduce VO, then the drain source voltage or the source drain voltage, to be more precise, the source drain voltage of the PMOS increases as VO is reduced, and so the current in the PMOS increases. And if it is initially in triode because the source drain voltage is small, but after a certain point the transistor goes into saturation. So here this is the PMOS in saturation, and of course because it is in saturation it has a very shallow slope, and so does the NMOS, and therefore we can get a nice high voltage gain from this circuit. Alright, so this is called the CMOS common source amplifier. So now let us study this in some detail. So first we need to bias these so that both the transistors are in saturation, and we have seen this circuit before, one of the DC analysis lectures, I forget which one. So we want to make sure that, well, if VG1 is 0.9 volts, then we want to make sure that VG2 is such that M2 is also in saturation. And we saw that well, the numbers we are using are such that mu n Cox W by L is the same as a mu P Cox W by L, and therefore for these to carry the same saturation current, the source gate voltage of the PMOS must be the same as the gate source voltage of the NMOS. We've seen this before. So if this is 0.9, this also must be 0.9, and so we make VG2 equal to 2.1 volts. And with these gate source voltages, the drain currents will be equal and they'll have a value of 0.5 milliamps. I'm repeating this because we've discussed this circuit before. We also found that when both these transistors are in saturation, the drain voltage cannot be determined exactly. It is a high impedance node. So to be safe, we'll just say that VO can be in the range of 0.5 to 2.5 volts. But we don't know the exact DC value of VO because both transistors are in saturation. Alright, so this is our DC design. Now we apply an AC voltage and we find the voltage gain. So we say let VG1 be equal to the DC plus a small AC, and now we do a small signal analysis. So in order to do a small signal analysis, we'll draw the small signal circuit. So, but we have not seen the PMOS small signal circuit before. So here it is. It is of course very similar to the NMOS circuit, only all the polarities are reversed. So the source is at the top, gate, drain, and in the small signal circuit, the source will be also drawn at the top. Source to gate voltage, the gate is floating. The GM current source is GM VSG, and it is pointing from the source to the gate. Alright, so it is again up to you. This is what I am used to and I use, but it is equally correct to draw this as GMVGS pointing upwards. Alright, it's your choice, it doesn't matter. As I said, I prefer this because the SG, the source gate voltage in a PMOS, is positive, and positive is intuitively easier to visualize. So, okay, so we have GMVSG from source to gate, RO, and GMBVSB. And for our circuit, the source will be shorted to the body. For a PMOS, the body will be shorted to the source, the highest voltage in the circuit. So the GMBVSB term will be 0. Alright, so with this, why don't you pause this video and derive an expression for VO by Vin. Alright, it is straightforward, but spend a couple of minutes. Okay, I'll continue. So here is a small signal circuit. Let us think about this. So the input is applied between the gate of M1, G1 and ground. GM1 Vin is the NMOS dependent source. RO1 is the resistance, output resistance of the NMOS. Vin, of course, because VGS1 is equal to Vin. For the PMOS, in fact, maybe let's go back to here. So for the PMOS, the gate is DC, the drain is DC. So VSG in the small signal circuit is 0 because both the voltages are DC. And so the only thing that stays for the PMOS is RO2. The GM-VSG current source is 0. Alright, and then RO2 is connected from the drain node to ground. So I've indicated all the nodes which are connected because this is the first time we are drawing this circuit. Over a period of time, of course, we'll stop pointing out which node this is. Alright, so we have GM1, RO1 of course is in parallel with RO2 because they are both connected from the output node to ground, and therefore we get the voltage gain as minus GM1 RO1 parallel RO2. So the first thing we note is that for the circuit where the load was a resistance RD, we had GM1 RO parallel RD, and RD usually was much smaller than RO, and therefore we got a gain of minus GM1 RD for the circuit with a resistive load. Now we have R01 and R02, and both will be of the same order, number one. Number two, both will be much larger than RD, and therefore that is why, of course, we get a higher gain from this circuit than we get from a circuit with RD. Alright, let us do some mathematics here. So minus GM1, R01 parallel R02. GM1 is 2ID over VOV, VOV1 for the NMOS. RO is 1 over lambda ID, RO, so 1 over lambda 1 ID, 1 over lambda 2 ID. The drain current is the same in both transistors, so we simply write ID. Now this 1 over lambda 1 ID is the resistance, so the conductance of the RO is lambda ID, lambda 1 ID and lambda 2 ID. So if two resistors are in parallel, the conductance is add, so we write this expression, and of course the ID cancels, and therefore we get the expression for the voltage gain of this circuit as minus 2 over VOV1 into lambda 1 plus lambda 2. Now it is important to recognize and note again that the drain current cancels. Alright, it is important because if we look at this expression and if we were to think about ways of increasing the gain, we'll say, well, one way of increasing the gain is GM, and one way of increasing GM is to increase the drain current, because this is 2ID over VOV. One would think that one could kind of go on that logical line. So for a VOV1, one could increase the W by L to increase the ID, and one would hope that if in ID is increased, the GM will increase and so the gain will increase. But it turns out, looking at this mathematics, that increasing ID has actually no effect on the gain, because although GM increases as ID increases, ROs decrease as ID increases, and the effects cancel out. So two things, therefore, ID has no effect on the gain, alright, and so there's no point changing ID to increase the gain. The other is, what is the other thing? Which is the same thing I'm saying in a different way, that whatever current may be flowing in this circuit, the voltage gain will remain the same. Alright. So, okay. Now again, but of course this is also true only for this set of equations which assume that lambda is not a function of ID. Alright, in real life lambda is actually a function of ID, as you will see in your first assignment, or maybe you have already seen in your first assignment, that lambda does change with ID. Alright, so but to first order or zeroth order, this is true, that the current has very little effect on the gain. You will see that lambda actually increases as lambda increases as ID increases, and therefore the gain actually decreases as ID increases. Okay, all right. Anyway, let's those effects let's not think about now. So we say this is the expression, and we'll focus on this right now, not worried about ID. So we ask the same question as we asked last time with the RD circuit. How do we increase this voltage gain? So of course now it is very simple to answer that question. We say, well, if we want to increase the voltage gain, we have to reduce VOV and we have to reduce the lambdas. Alright, VOV we've already discussed last time. The minimum VOV we can use for any MOSFET circuit is 0.1 volt. So the largest gain we'll get for this circuit with respect to VOV is when VOV is made to be 0.1 volt. By the way, this is VOV1, right? This is the VOV of the NMOS, the driver transistor. The PMOS, which is a load transistor, the overdrive of the PMOS does not affect the voltage gain. That's an important thing to remember. Alright, so let us say we reduce VOV to increase the voltage gain. All right. So what is the, let's think again, what is the effect of reducing VOV on the circuit other than increasing the gain? The effect is that reducing VOV will reduce the current, because the current goes as a square of VOV. And suppose I want to increase the current. I reduced VOV, current reduced, but I want to make the current larger. How will we make the current larger? We'll increase W by L. Alright. So as we reduce VOV, gain increases, current decreases, we can increase W by L to increase the current. What is the effect of increasing W by L? Increasing W by L increases capacitances, which of course we'll study after a few lectures. Alright. So with our number, so we have a lambda of 0.05. So the lowest point VOV is 0.1. So we can get a gain of minus 200 from this circuit, and the gain was minus 60 for the circuit with RD. So we've got some improvement in the gain by using the PMOS load. Can we increase this gain further? It is 0.05 lambda and VOV is 0.1. Can we do something to increase this gain further? We can reduce lambdas. How do we reduce lambdas? We increase the channel length, right? We saw this many lectures ago, that the channel length modulation is a function of the length. So the larger the length, the smaller is the effect of channel length modulation, and therefore lambda is smaller as the length increases. So we can increase the gain further by increasing the channel length. Alright, what is the effect of increasing the channel length? Again, capacitance is increased, because when we increase L, we'll have to increase W by the same proportion to keep the current constant, and so both W and larger will mean increased capacitances. Alright, let us think of, okay, let me make some broad comments about this. So the first thing I want to say is this common source, CMOS common source amplifier is the kind of the basic building block of most MOSFET amplifier circuits. Alright, in fact this will be our main circuit that will extend and expand to make higher and higher gain amplifiers, and this is true for most MOS amplifiers that are designed in the world. The CMOS amplifier is the foundation for building high gain amplifiers. They usually, MOS amplifiers don't have resistive loads unless you want the gain to be small, right, 10, 20 like that, then you will use a resistive load. I want to talk about the channel length modulation. So let's go back to this here, or this one. So what this is telling us, so the first, as I said, this expression is now fundamental for us, because this expression is the expression of our fundamental amplifier circuit, the CMOS common source amplifier. Now we say, okay, I want high gains from my CMOS common source amplifier, therefore I must have lambda small, right? Now lambda small means that the length must be large, alright? And if the length is, okay, so here is the thing, as I had mentioned a few lectures ago, over the last 50 years, channel lengths of MOSFETs have been shrinking by a factor of 2 every 2 years, at least until about 2002 or so, then it slowed down, but so we've come from tens of 100 microns to tens of microns to a few nanometers now. And the reduction in channel length, and therefore basically the reduction in the dimension of MOSFETs, has been all wonderful for digital circuits, because digital circuits digital circuits work faster when the channel length is smaller, because dimensions are smaller, the resistances are smaller, the capacitances are smaller, so they work faster. Because the transistors are smaller, you can put many more transistors on a chip, and therefore the amount of system one can build on a chip becomes larger and larger. Again, because the sizes are smaller, the power dissipation or the power consumption is less, because the power goes as half C VDD squared, where C is the capacitance, and because the capacitance is reduced, the power is reduced. So shrinking in technology has been just a blessing and wonderful for digital circuits, not true for analog circuits. And channel length modulation is one of the fundamental reasons why shrinking has not been good for analog circuits, because for analog circuits, or specifically amplifiers, the one thing we want is a large gain. But as channel length becomes smaller, this lambda becomes larger, and because it becomes larger, the gain becomes smaller. Therefore, analog circuit designers do not use 20 nanometer channel lengths while designing amplifiers. Even in a 20 nanometer technology, which means that I have the capacity to design or fabricate 20 nanometer channel length MOSFETs, the analog circuit blocks, so most ICs today will have a large digital system and a few small analog blocks on the same chip. The analog blocks will not have channel lengths of 29 nanometers. They will have much larger channel lengths because we need larger gains. Alright, and larger gains need smaller lambdas, which need larger channel lengths. Alright, so please remember this. I often come across even not just students, but I mean some academicians also, who, in the order to appear cool, will kind of tell students, well, why don't you use 20 nanometers? You are using 180 nanometers. You should use 20 nanometers in your designs. Acceptable for digital circuits, not correct for analog circuits. 20 nanometers is cool for digital circuits. It is totally uncool for analog circuits, specifically amplifiers, because you will not get any gain. You will probably get a gain less than 1 for a 20 nanometer MOSFET. Alright. Okay, so that is an important note here. Another small note. So for this amplifier we just studied, we had applied the input signal to the NMOS. Theoretically, one could apply the input either to the NMOS or the PMOS. There is a symmetry there in the circuit. So once the DC circuit is designed, we can apply the input to the gate of the PMOS or the NMOS. Now there are different considerations that decide in an actual application where one would apply the input, whether to the PMOS or the NMOS. The PMOS has a lower GM compared to an NMOS for the same size, right? Because the PMOS has a lower mu-p Cox, or mu-p specifically. The mobility of holes in silicon is lower than the mobility of electrons in silicon, and therefore mu-p is smaller than mu-n, and therefore for the same size transistor, the PMOS will carry, and say the same DC biases, the PMOS will carry a smaller current. So that is a disadvantage. The advantage the PMOS has is that it turns out that due to the very difficult and detailed physics of how holes behave at the interface of silicon, the PMOS produces less noise compared to the NMOS. So if one wants high speed, then one chooses NMOS, because the size of the NMOS will have to be smaller, and therefore it will offer less capacitance to the incoming input signal. But if one wants low noise, then one chooses a PMOS input. Alright. For high speed low noise, NMOS is generally preferred, uh, even though PMOS has a lower noise, but that is again, that's an RF issue that maybe you will study next semester. All right. Okay, so that is the end of this lecture. Next lecture we'll talk about amplifier performance parameters, input resistance, output resistance specifically, and then we'll do a quick design of the CMOS, a common source amplifier we have just studied.